So the preview activity in this section was just designed to get us used to the idea of parametrized curves. So what it asked us to do was just to sort of plot some vectors, and what all of these different vectors have in common is that they all kind of arise from the same functions of a single variable. So cosine of something, comma, sine of something. And so in parts A and B, you plotted those points where what the inputs were integer multiples of pi over 2, and in part B they were integer multiples of pi over 4, odd integer multiples of pi over 4. And so when you did those plots, what shape ended up emerging when you plotted those points in this preview? Yeah, if you plotted all 8 of these points, what you probably noticed is that they all lie along a circle. And so one of the things that really helps in doing any sort of work with parameterized curves is having some technology at your disposal to be able to not just see a few points and compute all of their coordinates by hand, but to make the best use out of technology to be able to see a bunch of points and not have to think too hard. So the t equals 0 point is over here at 1, 0, 0. And as t evolves in time, whoops, I guess I do have to zoom out a little bit. T equals pi over 4 ends up being right here. T equals pi over 2 is up there. 3 pi over 4. Pi itself, so and when t was equal to pi, we ended up at this point negative 1, 0. And then 5 pi over 4, 3 pi over 2, 7 pi over 4. And that by the time we get back to 2 pi, we have closed up this entire circle. So what we might say is that if I have a vector-valued function whose x component is the function cosine of t, and whose y component is the function sine of t, then as t ranges from 0 to 2 pi, that vector-valued function's range, if you like, its image, is going to be a curve in the plane, and that curve is going to be a circle. So one of the jobs that we might want to do with this kind of work is to figure out how to relate that parametric equation, that vector-valued function, to various other ways that we have of understanding the set of points that that vector-valued function is parametrizing. So for example, since we have in this problem the parameterization, I'm going to call it vector r of t is cosine t comma sine t. So this was my parametrized curve, and we think that this is going to trace out a circle. By the way, what's the radius of this circle? Apparently. It looks like it's centered at the origin, and its radius would be
1.
Well, it looks like 1. Yeah, it looks like that this is just the unit circle, right? Everybody's frenemy from trigonometry, the unit circle. And so what we might ask is what are some other ways that we understand the unit circle, and how could we know that this parameterization is actually connected to the unit circle in some way? Like, what is another way to describe the unit circle that we know? If you reach into your memory bank. Is there a Cartesian equation? So an implicit equation in the variables x and y.
Well, you could say like x squared plus y squared equals 1.
Yeah, exactly. X squared plus y squared equals 1. So here are two different kinds of equations, right? A Cartesian equation, which is implicit, right? It doesn't tell me the coordinates of any points. It just tells me what relationship the x and the y components of those coordinates have to satisfy, right? As long as the x coordinate squared plus the y coordinate squared is equal to 1, that point will belong on the unit circle. Meanwhile, our parametric equation, our vector-valued function up here, this is a parametric, is explicit, right? It actually tells us the coordinates of points. All we have to do is supply it with a t, and it's going to spit out for us the coordinates of some point that belongs on this parameterized curve. So let's just take a brief moment and see if we can figure out how might we know that there is a relationship at all between these two. Why is it reasonable to expect, and here I'll try to ask this really carefully, why does r of t parametrize the unit circle? How could we sort of investigate that question? How can we bring these two different descriptions together? Let me rephrase this in a slightly different way. Why does every point r of t satisfy the unit circle equation x squared plus y squared equals 1? That's my alternative framing for this question. If I'm unsure about this, what could I do? Well, what's playing the role of x in my parametrized curve?
Cosine?
Yeah, cosine t. And the role of y is being played by sine t. So sometimes instead of using a vector-valued function for a parameterization, if you meet parametric equations in a single variable calculus class, sometimes they're written out as something like x of t, y of t, right? X of t is cosine t, and y of t is sine t. If you don't have the language of vectors, as you don't in single variable calculus, usually this is what a parametric function looks like. And so if I want to know why all of these points satisfy the equation x squared plus y squared equals 1, I'm really asking, well, if x is equal to cosine t and y is equal to sine t, then is it true that x squared plus y squared is going to equal 1? All we would have to do to investigate is just to substitute. Plug in, which is a phrase that math teachers despise sometimes. But so I would just take, and in place of x, I would put cosine t. And in place of y, I would put sine t. And then if we'll just put sine t in place of y. And so x squared plus y squared, once we make that substitution, is cosine of t quantity squared plus the sine of t quantity squared. And what do I know about that expression?
Igual a 1?
It's equal to 1.
It's equal to 1 regardless of the value of t. And that's, one of the places where trigonometric identities are going to come in handy, right? This is an identity for all t. And so it ends up checking out, right? That all of the points which can be described by x being the cosine of some t and y being the sine of that same t, right? All points that have that description do lie on the unit circle, x squared plus y squared equals 1. Because this squared plus that squared is always equal to 1 regardless of what the value of the parameter t is. So one of the things about parameterizing curves and surfaces is probably the most important thing about parameterizing curves and surfaces, honestly, is this interplay between a parametric description, an explicit description of the points that lie on the object of interest, and implicit equations that describe those same things. There is not, in general, kind of a recipe, usually, for going from one of these to the other. If we have both of them, so a parametric equation and an implicit equation, we can usually just evaluate, substitute one of them into the other to determine that there is some match, right? But it's not always obvious if we're given one of these how to find the other one. And some of that's going to be a process that we're going to work on a lot. It's going to be with us all semester. And so as we go along, we're going to pick up little tips, tricks, techniques. On most of the time, what we want to do is go from an implicit equation to discover a parametrization of it, right? So go from x squared plus y squared equals 1 to discovering r of t equals cosine t sine t. And even just this example, I think, demonstrates how not obvious it is, because this original equation doesn't have anything to do with trigonometry. If you just hand me x squared plus y squared equals 1, unless I knew up front that trigonometry was involved in some way, I would have no reason to think that there's anything trig happening here. This looks like it's just an algebraic equation. So that's going to be one of the things that we work on consistently throughout the course, is developing some of those tips and tricks and techniques. One of those tips and tricks is going to be to use different coordinate systems. So one of the ways to do this step here is to think about, instead of using rectangular coordinates, using polar coordinates instead. Instead of x's and y's, we could use r's and thetas. And that ends up being one fruitful avenue toward parametrizing curves. Anyway, so that was much more sort of detailed, I think, than this preview activity was trying to get at. Really, the point of the preview activity was just to connect this vector-valued function with that idea that the various values of t in that vector-valued function actually do sweep out a curve inside of two-dimensional space. And in this particular example, that curve happens to be a circle.